So welcome to the second video of the lecture number 18. Okay, so in this video we will talk about the generator load model, because we know as the load on a generator changes, or power demand changes, the speed of the rotation of the generator, it also changes, that is frequency will change. Okay, so in this lecture we will discuss about the generator load model, and then we will discuss about how to complete this whole block diagram of a power system. Okay, because in the power system we have load, we have generator, we have turbine, and we have governor. So far we have discussed about the governor and turbine, but let us discuss about the generator and load now. Okay, so it is easy. Okay, so next is generator load model, lecture 18. Generator load model. So this generator load model, let us first discuss, what happens when this load on a system changes. If a load on a system changes, what happen? The generation of the system, the power that is generated by the generator, it also changes. Okay, so why it changes? Because the frequency of the system, it will change. Okay, so I'm saying this generator load model, it gives a relation between the change in frequency del f. Why frequency changes? It gives a relation between the change in frequency del f as a result of change in generation, delta Pg, and when this generation will change, when load changes by small amount, I will say by small amount, suppose delta Pd. Okay, sorry, this is delta Pd. I'm saying when demand changes, okay, because of the change in demand, the generation will change, and because of generation, frequency will change. Okay, so if I will neglect the losses in the generator, so I'm saying if I will neglected the generator losses, I will say whatever was the turbine power, change in turbine power output, it was equal to the change in generator output. Okay, so this is equal to this. Okay, but I'm not saying this demand is equal to generation. Okay, change in demand is equal to change in generation. I'm saying change in turbine power is equal to the change in generator output, but change in generator output is not equal to change in demand. So I'm saying if neglecting the generator losses, delta Pg is equal to delta Pd, and net surplus power at the bus bar where generator is connected, surplus power will be given by net surplus power will be equal to what? Suppose generation has changed by delta Pg and the demand has changed by delta Pd. So difference between the change in generation and change in demand, it will give me the net incremental power or net surplus power. Okay, where what is delta Pg is the incremental turbine power output. Okay, delta Pg is the incremental turbine power output, because I'm saying that losses are neglected. So delta Pg is what? Delta Pg is the incremental turbine power output, and surplus power is delta Pg minus delta Pd. Okay, now this surplus power or increment in power input to the system is absorbed in two ways. This is surplus power that is in the system. So this can be absorbed in two ways. Number one, how it can be absorbed? I will say that it will increase the kinetic energy of the generator rotor. Okay, increases the kinetic energy of generator rotor, means the speed of rotation of the rotor will increased. Okay, so at scheduled frequency, suppose I am saying when frequency was, it is f naught is a nominal. nominal or scheduled frequency f naught. Okay, so can you tell me, do you know what is inertia constant h? Kinetic, it is a kinetic energy stored in rotor at synchronous speed divided by rating of machine, rating of machine. Okay, suppose I am saying this kinetic energy stored in rotor at synchronous speed. Synchronous speed means the speed at which we are getting frequency equal to f naught. Okay, so from there I can write this kinetic energy at synchronous speed is represented by W K E naught. At synchronous speed means when frequency was f naught. So it will be equal to h into PR, where PR is nothing but the rating of machine or rating of generator, and h is the inertia constant. Okay, so this is the kinetic energy stored in the rotor at synchronous speed. Okay, so tell me, kinetic energy, it is proportional to square of speed of rotation. Okay, I'm saying this kinetic energy is proportional to the square of speed of rotation, and speed of rotation represents nothing but frequency f. So hence I can say that at nominal frequency, speed of rotation was W K E naught. Okay, and at frequency, when the frequency was f naught, I am saying stored kinetic energy was W K E naught, and when frequency changes by some small amount delta f, which is given by new frequency is given f plus delta f naught. Okay, it is will be proportional to W K E. Okay, so this kinetic energy is proportional to the nominal frequency, and this kinetic energy is proportional to the new frequency, which is nothing but the nominal frequency but plus change in frequency. Okay, but proportionality is proportional to the square. Okay, so I can write it in simpler words. I can write it as that kinetic energy at any frequency divided by kinetic energy at nominal frequency. So it is proportional to f naught plus del f divided by f naught square. So if I will open the terms, I will get W kinetic energy at any frequency is equal to kinetic energy at nominal frequency. If I will solve these equations, I will get 1 plus twice delta f by f naught plus some higher order terms. Now this del f is a small change in frequency. Okay, so del f by f naught, it will be very small. So I will neglect the higher terms and I will get kinetic energy at any frequency is equal to kinetic energy at nominal frequency into 1 plus twice del f by f naught. Okay, now here we calculated the kinetic energy at nominal frequency. Okay, it was h into the rating of the machine. Okay, so can I write it here that kinetic energy at any frequency is equal to h into the rating of the machine 1 plus twice del f by f naught. Okay, so this is the kinetic energy stored in the rotor at frequency f naught plus del f. So rate of change of kinetic energy, this rate of change of kinetic energy with respect to frequency, it will be what? Rate of change of kinetic energy will be equal to d by dt W K E. So this is constant, it will be 0. So it will be equal to twice h rating of the machine divided by f naught into d by dt of del f. So rate of change of kinetic energy, it will be proportional to the rate of change in frequency. Okay, so this is one. So I'm saying the surplus power is absorbed. Number one, it increases the kinetic energy of the rotor of generator. Okay, number second, you know these motor loads, they are frequency sensitive loads. Okay, so as frequency changes, the motor load will change. Okay, because this motor load, it is sensitive to frequency or speed. So I'm saying that motor load is sensitive to frequency. So as frequency or speed changes, okay, the motor load will change. So the rate of change of load with respect to frequency, I'm saying now that rate of change of load del PD divided by del F. Rate of change of load with respect to frequency, it can be regarded as constant if the change in frequency is very small. If the change in frequency is very small, so I will say that the rate of change of load with respect to frequency is nearly constant. Okay, del F by del F is nearly is neglected, can be regarded as or nearly constant as constant for small change in frequency. Okay, if the change in frequency is very small, so I will say that this this change in load with motor load with respect to frequency, it is nearly constant. So if I will use the sign del PD by del F to delta F, it will be equal to nothing but B into del F, where B is nothing but del PD upon del F. So where B is a constant, where B is a constant and B is the area parameter, and the units are B. If you will see, it is megawatt per hertz. Units of B are megawatt per hertz, and this B, it is means determined empirically. B, it is determined empirically. You almost know what is empirical formula. Empirically, and B is positive for motor load. Okay, so I am saying the motor load will change if the frequency changes. Okay, because the motor load is sensitive to the change in frequency or speed, and the rate at which and the rate of change of load with respect to frequency, the rate of change of load, I'm saying the rate of change of load with respect to frequency, it can be regarded as nearly constant for small changes in frequency. Okay, I'm saying rate of change of load, rate of change of load with respect to frequency is equal to B delta F, means this I am representing this by a constant if the change in frequency is very small. That is what I am writing. The rate of change of load with respect to frequency can be regarded as nearly constant for small changes in frequency. So I am replacing this with the constant B for small change in frequency delta F. Okay, so now I have two terms. I told you that first the net surplus power, it will be absorbed in or utilized in two ways. Number one, it will increase the kinetic energy of the rotor, and second, it will increase the motor load. Okay, so I will say that net surplus power was delta Pg minus delta Pd. Change in generation because of change in demand is nothing. It can be utilized in two ways. The first term is twice H PR divided by F naught d by dt of delta F, and the second term is the change in the motor load plus beta delta F. Okay, got it? Now if I will divide the whole equation by this PR is the rating of the machine, what will I get? So dividing the whole equation by PR, I will get delta Pg in per unit minus delta Pd in per unit is equal to twice H upon F naught, okay, d by dt of delta F plus beta in per unit multiplied by delta F. Got it? So you have no, this whole equation is in per unit. Got it? But I will not use per unit in the following equations because it will increase the complexity. Okay, but you will it is understood that the whole equation is in per unit. So next, delta Pg minus delta Pd. Now I am taking it in Laplace. I will take the Laplace of the above equation. Delta Pgs minus delta Pds will be equal to twice H upon F naught. So Laplace of a derivative, it is nothing but S into delta Fs plus beta into delta Fs. So this is the equation. Now take delta Fs common. So you will get delta Pg S minus delta PDS will be equal to twice H divided by F naught into S plus beta into delta Fs. Okay, so what is delta Fs equal to? So if I will see, delta Fs will be equal to this term divided by this. Okay, so delta Fs will be equal to delta PGS minus delta PDS, okay, whole divided by beta plus twice H upon F naught into S. Okay, so take beta common, B common in the denominator. So what are you left with? Delta PGS minus delta PDS. So 1 by beta is common. What I am left here with, it is 1 plus twice H into S divided by beta F naught. You got it? So delta Fs I will write now. Delta Fs I will replace this is now by some terms. So 1 by B is nothing but KPS. Okay, gain of the generator or power system whole, I can say KPS what I'm left here, I am delta PGS minus delta PDS, okay, divided by 1 plus S into TPS. So where KPS is the gain of the power system, gain of the system or system gain, it is system gain, and it was given by 1 by B, and TPS is nothing but the time constant of the power system time constant, and this was equal to twice H divided by B F naught. Got it? And this gain of the power system is of the order of 20 seconds. Okay, gain of the power system is of the order of 20 seconds. Now we have we derived in the previous video, I derived the block diagram, where we were having a turbine. If I ignore this block, whatever is on this right side of delta XES, so I am left with the turbine, this Gorner model. So after joining this, so I will get turbine and Gorner and turbine model. Now I am assuming that there are no losses, so I am saying that the change in turbine power is equal to the change in generator output delta PG. Okay, and this delta PG, taking the delta PG into consideration, I am getting the output is getting delta Fs, and you can see the delta Fs is here as the feedback, change in frequency is the feedback. So I will complete the whole diagram and I will show you. Firstly, I will draw this part of the diagram, this much of a diagram, but I will use another page for that, obviously. So firstly, initially I have what? I have the Gorner delta PCS, which is nothing but this, it represents speed changer. Then I have this 1 by R, and here I have delta Fs. Okay, so here what I am getting, here is my Gorner KSG, small g represents Gorner, 1 plus S TSG. So the output of the Gorner is delta XES, so which is the input to the turbine. Turbine is KT plus 1 plus S TT, and the output of the turbine is delta PT, which is nothing but delta PG, because I am ignoring the losses or neglecting the losses. So if you, this completes this diagram. Okay, so I have Gorner, this is my Gorner, this part is my Gorner part, and this is my turbine. Now I will connect the generator. Okay, so the equation for the generator, if you will see, it is the equation for the generator, it is this where I have drawn complete equation here. Yes, KPS upon 1 plus TPS. Okay, but what is the input to the generator? It is delta PG. The first input is delta PG, if you will see here, and the another is delta PD. So this is delta PG plus another is delta PD. So I will say delta PD minus here is delta PDS. So this is the input So this input is going into the transfer function block with the gain kps upon 1 plus s time constant tps. And what is the output of this block? It is nothing but delta fs, and this delta fs is the feedback to the speed governor, delta fs. Okay, got it? So this is the complete block diagram of the for a load frequency control of an isolated power system. So what is this? This is the complete block diagram of for load frequency control of an isolated power system. Okay, so here this part is the governor. So okay, so the governor obviously will sense the change in speed, which is nothing but the change in frequency, and it will take the appropriate action. So the because of the change in speed, the frequency will change. There will be some displacement in the linkage mechanisms. Okay, so the valve, steam valve will open or close according to the frequency deviation. If the frequency, whether the frequency is reducing or frequency is increasing. So then we have, this is the turbine block. Okay, this is turbine block, and then this is the generator block, and input to the generator is nothing but pt minus delta pd, and this represents the load. So this is the load frequency control of a single area power system. Okay, got it? So this is the load frequency control of a single area power system. Okay, so from the block diagram, if you can see from the block diagram, hope the whole diagram is visible. Okay, yes, it is now visible. Oh, or I should rotate, I should rotate it by 90 degree. Okay, if you can see from the block diagram, we observe there are two important incremental inputs. This is the load frequency control diagram of a single area power system, and in this diagram we have two important incremental inputs to the system. So what is the two important inputs? First input is the change in the position of the speed changer, delta PCS. Okay, change in the position of the speed changer, and the second is the change in demand, delta PD. Okay, so what if I am saying that change in the speeder position, speed changer, change in the speed changer position, it is fixed. It is fixed means we are keeping delta PC is equal to 0. If the change in the position of the speed changer is fixed, delta PC will be equal to 0, and that at that time we will say that it is a governor free action, because the governor is not acting at that time. Okay, so let us calculate what will be the how the system will behave for a governor free action. So what I am saying when the speed changer setting is fixed, means when delta PC is equal to 0, but there is change in demand in the system. Okay, so when there is change in demand in the system, but because we have kept the change in the speed, this speed changer setting, we have kept the speed changer setting fixed, so delta PC will be equal to 0, and it is called as governor free action. So I am saying for governor free equation, for governor free action means delta PCS is equal to 0. Okay, are you getting? So for such an operation, the steady change in system frequency, system frequency del f, okay, for sudden change in load demand delta PD, okay, it is given by obtained as, I am saying it is given by, I have written it somewhere. Okay, I will see. I am saying this is 0. I am saying this is 0, but frequency is changing because of the change in demand. Okay, at that time delta Fs will be equal to what? If you will see, delta Fs will be equal to what? Delta Fs will be equal to Kps. Okay, at that time the system will behave like, I will, let me draw. I am saying this whole will be in the feedback then. Okay, yes, I'm saying yes. I'm saying this is my kps upon 1 plus s tps, and this is the delta fs. Okay, so what I am doing, I'm saying when load demand changes, but this is kept constant. What speed changer setting is kept constant. So this is delta pds, this is positive, sorry, this is negative. Okay, and this whole will act in a feedback. So what is the feedback? 1 plus, okay, so this whole will act in the feedback. No, so in the feedback I have ksg into kt divided by ksg into kt divided by 1 plus s tsg into 1 plus s 1 plus s t tt. Okay, these two are in series, plus 1 by r into minus 1 by r, and then what is here? It is delta f, as the system will get reduced like this. Okay, so how the system will behave now? If you will say no, then delta fs for a Gorner-free equation means when delta pcs is equal to 0, it will be equal to minus kps divided by 1 plus s tps plus, it is nothing but k. If you will see, it was suppose it was g and this is whole h, it is g upon 1 plus so I will directly write down, I will not write down the form 1 plus kps into kt, okay, into ksg by r, okay, divided by 1 plus s tps into 1 plus s tsg into 1 plus s tt. Got it? So if I will solve this further, what will I get? I will get del fs when delta pcs was equal to 0. So I will get this equal to minus kps whole divided by, this is 1 plus s tps. So I will get 1 plus s tps. What am I left with? I'm left with kps kt into ksg by r divided by 1 plus s tsg into 1 plus s tt. Okay, so what is I am left with here? I am left with here delta pd by s. Okay, here also multiplied by delta pd by s. Okay, so you know that kt is fixed for turbine and kps is fixed for a power system. For kt turbine it is 1, and kps for power system it is 20. Now ksg, the speed Gorner, the gain of the speed Gorner ksg, okay, we are saying it is easily adjusted. Since this and this are fixed, we can easily adjust this so that ksg and kt is equal to 1. Okay, and we also know that kps is nothing but 1 by b, and what is b? B is nothing but rate of change of this frequency sensitive load with respect to frequency. Okay, so for before that, what we do, we will apply initial value theorem here. So if I will apply that theorem, what will I get? I will get delta f steady state when delta pc was equal to 0. This is the steady state. So it is given by limit s approaches 0 s of fs. Okay, when delta pc was equal to 0, to determine the steady state, we apply final value theorem here. Okay, and what will we get? We will get delta f is nothing but minus kps divided by 1 plus kps into kt into ksg divided by r into delta pd. So I am saying since kps is fixed for a power system and KT is fixed for a turbine. No, I can easily adjust KSG so that the product KT and KSG is equal to 1. Okay. So, and I also note that the KPS is nothing but 1 by B, and B is nothing but it is the rate of change of change in demand, motor load, because of the change in frequency. So I can write it as this as del F as minus, instead of KPS I will use B. Okay. 1 plus, no, I can adjust this term to make this term equal to 1, whole term equal to 1. So it, I am what I am left here, I am left with 1 by R. Okay, into what? Into delta PD. Okay, am I right? Into BR. Okay, because we have now here KPS is equal to 1 by B. So this B 1 by B multiplied by 1 by R. So it will be 1 by BR here. Okay. So next, let me get some sheets, blank sheets. I think this will be enough. So if I will solve it further, what will I get? I will get delta F is equal to minus 1 by B divided by BR plus 1 by BR into delta PD, or delta F is equal to minus BB will cancel 1 divided by, so it, if I will solve this, I will get B plus 1 by R into delta PD. So this term 1 upon B plus 1 by R, I am representing it by beta into delta PD, where what is beta? Beta is the area frequency response. Okay, it is the area frequency response characteristics, where beta is nothing but the area frequency response characteristics. I am labeling this equation as equation X. In short, beta is represented at AFRC, area frequency response characteristics. So I think I should stop this right here. Then tomorrow in the next lecture I will continue. I will continue this lecture forward, this topic forward. Okay, in the next lecture. Thank you very much.